Look up at the night sky. That vast expanse of stars and galaxies might be only the smallest fraction of reality. We are about to journey through 30 mind-bending theories that propose our universe is built upon hidden dimensions of existence. By the end, you will possess a new framework for understanding the very fabric of the cosmos. We will explore how black holes might encode information on their surface, and if our entire reality is a holographic projection. What single question about the universe keeps you awake at night? Our journey into the hidden layers of reality begins not with complex machinery, but with a simple, elegant idea born on paper. In the early 20th century, a German mathematician named Theodor Kaluza was studying Einstein's revolutionary theory of gravity, general relativity. He made a small, almost whimsical adjustment to Einstein's equations. He asked, what if we do not live in just 4 dimensions, 3 of space and 1 of time, but in 5? By adding this single extra dimension, Kaluza found something astonishing. The equations for gravity and the equations for electromagnetism, which had seemed completely separate, merged into one beautiful, unified description. It was as if a single, unseen dimension was the hidden key connecting 2 fundamental forces of nature. But this immediately raised a practical question. If a 5th dimension exists, where is it? Why can we not move through it or see it? This is where Swedish physicist Oscar Klein entered the picture. He proposed that this 5th dimension is not like the vast, expansive ones we experience. Instead, it is curled up into an unimaginably tiny loop, a process we call compactification. Imagine a garden hose stretching far into the distance. From a distance, it looks like a simple one-dimensional line. But if you get very close, you see its circular cross-section, a second dimension that was always there, just too small to notice with the naked eye. Klein suggested the extra dimension is like that, curled into a circle so minuscule that it remains forever beyond the reach of our most powerful instruments. While physicists eventually moved on from this specific theory, its profound legacy endures. The Kaluza-Klein Theory is the grandfather of all modern multidimensional ideas, planting the crucial seed that our universe's deepest secrets might be written in dimensions we have yet to perceive. That single, curled-up dimension was just the beginning. The next great leap in our understanding came from a theory so radical it reimagined the very building blocks of the cosmos. Superstring theory proposes that the most fundamental entities in the universe are not point-like particles, but incredibly tiny, vibrating loops of energy called strings. Think of a guitar string. A guitar string can vibrate in different ways, producing distinct musical notes. In a very similar way, a fundamental string vibrates at specific frequencies, and each unique vibration pattern manifests as a different particle. One vibration might be an electron, another a quark, and yet another the particle of light itself, the photon. In this framework, every particle we observe is simply a different note on the cosmic symphony of strings. But for this beautiful idea to work mathematically, the equations demand a specific stage on which to play. The universe cannot have only the 4 dimensions we know. For the math to be consistent and to include the force of gravity, superstring theory requires a total of 10 dimensions. That means, beyond our familiar 4, there must be 6 additional spatial dimensions, all curled up into an exquisitely complex microscopic shape. This theory also comes in several variations, like different models of the same profound instrument. There is type I, type Ia, type Ib, and heterotic string theory. Each version has its own unique mathematical properties, predicting slightly different particle symphonies. For decades, physicists have been trying to determine which, if any, of these versions describes our actual reality. Are we living in a universe built upon type Ia strings, or is the heterotic version the correct score? The search for an answer would lead to an even more ambitious and controversial idea. one that suggests a shocking possibility about the very nature of our cosmic home. The quest to find the one true string theory led to a stunning revelation. In the 1990s, physicist Edward Witten made a breakthrough that reshaped the entire field. He demonstrated that the 5 competing versions of string theory were not rivals at all. They were merely different perspectives, different windows into a single, deeper reality. He named this overarching framework M-theory, and it came with a profound new requirement. The mathematics of M-theory demanded not 10, but 11 dimensions. This 11th dimension was not just another tiny, curled-up loop. It opened up a vast new landscape of possibilities, transforming our view of the cosmos. Within this 11-dimensional framework, the fundamental objects are no longer just one-dimensional strings. M-theory introduces the concept of branes, short for membranes. These are multidimensional objects that can have many more dimensions than a string. A 0 brane is a point, a 1 brane is a string, a 2 brane is a sheet or a membrane. These objects can exist in higher dimensions as well, all the way up to a 9 brane. This new picture radically alters what our universe could be. Our entire 4-dimensional world of 3 spatial dimensions and 1 of time could be a 3 brane, a vast membrane-like surface floating within a higher dimensional space. In this scenario, the particles and forces we know might be confined to our brain, stuck to its surface like ink on a page. This single idea provides a potential answer to one of the universe's oldest mysteries, a question that has haunted philosophers and scientists for millennia. Why does gravity feel so weak compared to the other fundamental forces? Our universe might be a single slice in a cosmic loaf of bread. This is the brane world scenario, a powerful idea emerging from M-theory. In this picture, our entire 4-dimensional reality, all the galaxies, stars, and planets, exists on a 3-dimensional membrane, a 3 brane, floating within a much larger, higher dimensional space called the bulk. The bulk is the entire loaf, and our brain is just one slice within it. The crucial point is that most of the forces governing our daily lives, like electromagnetism and the nuclear forces, might be trapped on our brain. The particles of light and matter are like ink stains or seeds embedded in the bread slice itself, unable to leave its surface, but gravity is different. Gravity, described by Einstein as the warping of spacetime itself, might not be confined. It could be a force of the bulk, leaking out of our brain and spreading into the extra dimensions. Think of our brain as a sponge soaked with water. The water represents the familiar forces trapped within the sponge's structure, but if you place that wet sponge on a counter, a little water will seep out and spread across the surface. Gravity could be like that seeping water, not perfectly confined. This simple, elegant idea offers a stunning explanation for gravity's mysterious feebleness. The other forces are concentrated on our brain, intensely focused, but gravity dilutes its strength by spreading out or leaking into the vast expanse of the higher dimensional bulk. The reason gravity is so weak, quadrillions of times weaker than the electromagnetic force that holds atoms together, might simply be that it is operating on a much larger, multidimensional stage. This leads to a profound and slightly unsettling possibility. If our brain is just one slice in the loaf, what or who is on the other slices? Could there be other worlds, other universes, floating right alongside our own in the bulk, forever separate and unseen? This collision of worlds could be the very origin of our cosmos. The ekpyrotic universe model takes the brane world idea and transforms it into a breathtaking new story of cosmic birth. It proposes that our universe began not with a single, infinitely dense point, but from a violent yet controlled collision between our 3 brane and a neighboring parallel brane floating in the bulk. The immense energy of this impact was then translated into the hot, dense state we recognize as the Big Bang. In this model, the Big Bang was not the absolute beginning, but a dramatic turning point in a much older, potentially endless cosmic cycle. This offers a compelling alternative to the leading theory of cosmic inflation, which posits a period of unimaginably rapid expansion just after the Big Bang. Inflation was proposed to solve two major puzzles about our universe, the horizon problem and the flatness problem. The horizon problem asks why the universe looks so uniform in all directions. Distant regions on opposite sides of the sky have the same temperature, yet they seem too far apart to have ever been in contact given the age of the universe. Cosmic inflation solves this by suggesting these regions were once close together before a superluminal stretch pulled them apart. The flatness problem questions why the geometry of our universe is so perfectly balanced or flat between eternal expansion and eventual collapse. The ekpyrotic model tackles these same puzzles without requiring a period of hyper-fast inflation. Instead, the long, slow, parallel approach of the two branes before their collision provides the necessary conditions to create a universe that is both uniform and flat. The energy of the collision smooths everything out, just as two flat sheets of glass pressed together would expel any wrinkles or air bubbles between them. This leads to a truly profound possibility. If this cycle has happened once, it could happen again. Perhaps our universe is destined to cool, expand, and eventually be drawn back toward another collision, sparking a new Big Bang in an eternal, rhythmic dance of creation and rebirth. What if every event within a volume of space, every star, every planet, and every person, is merely a projection from information stored on a distant, two-dimensional surface? This is the startling proposal of the holographic principle, a concept that radically redefines the nature of reality itself. Its origins are not in science fiction, but in the deep and puzzling physics of black holes. In the 1970s, physicist Jacob Bekenstein made a profound discovery. He realized that a black hole's entropy, which is a measure of its hidden information or disorder, is not proportional to its volume as one might expect. Instead, it is proportional to the surface area of its event horizon, the point of no return. This was bizarre. It suggested that all the information about everything that ever fell into the black hole was not lost within its vast interior, but was somehow encoded on its two-dimensional boundary. Decades later, physicists Gerard T. Hooft and Leonard Susskind took this idea and ran with it, proposing that this was not just a property of black holes, but a fundamental principle of the universe. The holographic principle states that all the information describing a three-dimensional volume of space can be completely represented on its two-dimensional boundary, just like a hologram. A standard hologram is a two-dimensional piece of film that, when illuminated with laser light, creates a stunningly realistic three-dimensional image. The flat film contains all the data needed to reconstruct the full 3D scene. According to the holographic principle, our universe might operate on the same cosmic scale. The three-dimensional world we see and feel, with its depth and solidity, could be a magnificent projection from a vast, two-dimensional surface at the edge of the observable universe. Every particle interaction, every light ray, every thought you have might be a pixel in this grand cosmic display, translated from a flat, information-rich code we cannot directly perceive. This forces us to confront a dizzying question. Is the rich, three-dimensional reality we experience every day nothing more than an illusion? A shadow cast by a deeper, simpler truth written on a distant two-dimensional wall. But not every physicist is convinced that extra dimensions are the answer. A formidable challenger to string theory offers a completely different path to unifying the cosmos, one that rewrites the rules of reality without adding a single new dimension. This is loop quantum gravity. While string theory seeks to be a theory of everything by describing all particles and forces as vibrating strings, loop quantum gravity has a more focused yet equally radical goal. It aims to marry the principles of general relativity, which describes the large-scale universe, with those of quantum mechanics, which governs the tiny world of atoms and particles. Its starting point is to take Einstein's picture of smooth, continuous spacetime and break it apart. Loop quantum gravity proposes that space itself is not a seamless backdrop. Instead, it is woven from a fabric of incredibly tiny, finite loops. Think of a piece of cloth. From a distance, it looks like a single, continuous sheet. But up close, you see it is actually made of individual, interwoven threads. Loop quantum gravity suggests that spacetime is like that cloth, composed of a vast network of these one-dimensional loops. The theory quantizes space and time, meaning it proposes they come in discrete, indivisible chunks. There is a smallest possible unit of space, a tiny grain or atom of geometry, at the unimaginably small Planck scale. You cannot have half a unit of this space, just as you cannot have half an electron. This leads to a profound prediction. The smooth, continuous spacetime we experience in our daily lives is an illusion, an average effect of this underlying granular structure. Much like water looks like a continuous fluid even though it is made of discrete molecules. This granular nature of spacetime could resolve a major crisis in physics, the terrifying singularity at the heart of a black hole, where general relativity predicts gravity and density become infinite. In loop quantum gravity, you simply cannot pack matter into an infinitely small point because space itself is made of finite grains. This fundamentally different approach creates a stark contrast with string theory. String theory requires extra dimensions to make its equations work. Loop quantum gravity does its work entirely within the 4 dimensions we know and experience. It builds our universe from the ground up, from the quantum threads of space itself, rather than proposing that our world is a shadow or a projection from a higher dimensional realm. So we are left with 2 brilliant, yet seemingly incompatible visions of ultimate reality. One paints a picture of a cosmos filled with hidden, curled-up dimensions and vibrating strings. The other describes a universe where space and time are woven from a finite, granular fabric. Which one is true, or could both be different perspectives on a truth we have yet to fully grasp? While the battle between strings and loops dominates the conversation, a third contender offers a radically simple starting point. Causal dynamical triangulations takes the idea of a granular spacetime and asks a beautifully straightforward question. What is the most basic way to build a universe from scratch? Instead of strings or loops, this theory uses the simplest geometric shapes imaginable, triangles. More precisely, it models the fabric of spacetime as a vast, shimmering network of tiny, 4-dimensional triangular blocks called simplexes. Imagine these as the pixels of reality, but instead of being flat squares, they are the fundamental chunks of spacetime itself. The theory then lets these triangles connect to each other in every possible configuration, following only 2 basic rules. The connections must be causal, meaning cause must always precede effect within the structure, and the process must be dynamical, evolving step by step through time. When researchers run colossal computer simulations of this process, something remarkable happens. Out of the initial chaos of countless possible shapes and connections, a stable, large-scale structure consistently emerges. From a microscopic soup of jumbled triangles, our familiar 4-dimensional universe, with its 3 dimensions of space and 1 of time, crystallizes on its own. This is a profound departure from other theories. String theory requires 10 or 11 dimensions from the very beginning. But causal dynamical triangulations does not presuppose any dimensionality at all. It starts with simple building blocks and simple rules and watches as our specific reality self-assembles. The 4-dimensional continuum of general relativity is not the foundation, it is the final product. This suggests that the smooth, predictable spacetime we navigate might be a kind of collective illusion, an average effect of trillions upon trillions of tiny, causal interactions, much like the smooth surface of a lake emerges from the chaotic motion of countless water molecules. It presents a universe that computes itself into existence one tiny triangle at a time. The smooth, predictable reality we take for granted shatters at the quantum level. Here, the rules are governed by probability, where a particle can be in two places at once until we look at it. This bizarre behavior is captured by the Schrödinger equation, the mathematical heart of quantum mechanics. But what does this equation actually describe? For decades, the prevailing view was the Copenhagen interpretation, which states that the very act of observation forces a particle to choose a single, definite state from a haze of possibilities. It is a deeply unsettling idea, placing human consciousness at the center of the cosmic dice game. But there is another, even more mind-bending interpretation that removes the observer entirely. This is the many worlds interpretation proposed by Hugh Everett in the 1950s. Everett took the mathematics of quantum mechanics at face value. He suggested that the Schrödinger equation never collapses possibilities into a single outcome. Instead, every time a quantum event has multiple possible results, the entire universe splits, with each possibility playing out in a newly created, fully real branch of reality. Think of reality as a constantly forking path in a vast, infinite forest. You come to a branch in the trail, a quantum event. One version of you turns left while another version of you turns right. Both paths are equally real, but once the split happens, the two versions of you can never communicate or interact again. Every choice, from the decay of a single atom to the firing of a neuron in your brain, creates a new universe. This means there is a world where you never watched this video, another where dinosaurs never went extinct, another where you made that one different decision years ago and your life is entirely unrecognizable. In this framework, the multiverse is not a collection of distant alien universes with different physical laws. It is a sprawling, ever-expanding tree of possibilities, all stemming from our own quantum choices. These are not spatial dimensions we can travel to, but new dimensions of existence, entire timelines branching off into their own reality. The reason we only experience one timeline is that our consciousness itself splits, following just one branch of the endless tree, forever unaware of the other versions of ourselves living out every possible permutation of every possible moment. That branching tree of quantum possibilities is not the only vision of the multiverse. Another, even more expansive picture emerges from the very mechanism thought to have shaped our cosmic dawn, cosmic inflation. The theory of eternal inflation proposes that the rapid expansion of space did not stop everywhere at once. Instead, it suggests that the vacuum energy driving inflation decays randomly like water boiling. In most regions, the boiling stops and inflation gives way to the calm expansion of a universe like our own. But in other regions, the boiling continues, causing space to inflate at an unimaginable rate forever. Each pocket where inflation stops becomes an isolated bubble universe, forever disconnected from the others within the ever-inflating background. Our entire observable cosmos, with its hundreds of billions of galaxies, could be just one such bubble in an infinite, frothing sea of inflating space. This leads to a staggering possibility. The fundamental constants of physics, like the strength of gravity or the mass of an electron, might not be universal laws at all. They could be local bylaws set randomly when each bubble universe forms. In this cosmic landscape, some bubbles might have 4 spatial dimensions, others 5 or 10 or none at all. Some might have physics so alien that matter as we know it could never coalesce. Others might be stillborn, collapsing instantly. Our universe, with its 3 spatial dimensions and 1 of time, and its seemingly fine-tuned constants that allow for stars, planets, and life, would be just one fortunate possibility among an infinite number of failed or sterile realities. We do not live in a special universe, but simply in one that is habitable. The sheer immensity of this concept is humbling, suggesting that all we see and know is a single Chinese letter spark in an endless, chaotic fire of creation. An infinite multiverse of possibilities presents a profound puzzle. If countless universes exist with different numbers of spatial dimensions, why do we find ourselves in one with exactly 3? The answer might lie not in a fundamental law, but in the simple, stark reality of our own existence. This is the anthropic principle. It suggests that the universe we observe must be compatible with the existence of observers like us. We are not seeing a typical universe, but a very special one, because only in a special universe could life ever arise to ask the question. Apply this to the number of dimensions, and the logic becomes compellingly clear. The stability of atoms, planets, and stars depends critically on the precise way that forces like gravity and electromagnetism propagate through space. In a universe with only 2 spatial dimensions, gravity would follow an inverse distance law instead of an inverse square law. The consequences are catastrophic. Orbits would be unstable, and planets could not maintain a stable path around a star. A solar system in 2 dimensions would simply fly apart or collapse. Even the structure of atoms would fail to form. An electron could not maintain a stable orbit around a nucleus, meaning complex chemistry, and therefore life would be impossible. Now consider a universe with 4 large spatial dimensions. Here, gravity would follow an inverse cube law. Its strength would diminish so rapidly with distance that it could never pull matter together over cosmic scales. Galaxies would never coalesce from primordial gas, stars would never ignite, and the universe would remain a cold, dark, and featureless haze. The gravitational glue that builds the cosmos would be too weak to create anything at all. 3 spatial dimensions appears to be a cosmic sweet spot. It is the Goldilocks zone for reality itself, where gravity is just strong enough to form galaxies and stars, but not so strong that it crushes all structure. It is where electromagnetic forces can bind electrons to nuclei with the precise strength needed to create the 100+ chemical elements that make up our world. The 3-dimensional geometry of space allows for stable orbits, complex molecular structures, and the long, slow cosmic evolution necessary for planets to form and life to emerge. We do not perceive 3 dimensions because it is the only possibility. We perceive 3 dimensions because in a vast and varied multiverse, it is one of the very few configurations that allows for someone to be here to perceive anything at all. Our existence as observers actively selects for this specific dimensional stage. Our 3-dimensional reality might be just one act in an endless cosmic play. This is the vision of Roger Penrose's conformal cyclic cosmology, a theory that dares to suggest our universe has no true beginning and no final end. Instead, it undergoes an infinite series of cycles, each called an eon. Each eon starts with its own Big Bang and expands outward for trillions of years until all matter has decayed and black holes have evaporated through Hawking radiation. The universe becomes a vast, cold, and nearly empty void, populated only by massless particles like photons zipping through the endless dark. In this state of maximum expansion and minimum activity, a remarkable transformation occurs. According to Penrose, the universe loses all sense of scale. Distances and masses become meaningless concepts in this ultra-smooth, energy-less state. This property is known as conformal symmetry, a kind of geometric sameness where a universe of infinite size becomes indistinguishable from a universe of infinitesimal size. In this symmetrical state, the infinitely stretched end of one eon can be geometrically identified with the ultra-dense, ultra-hot beginning of the next. The death of one universe becomes the Big Bang of another, in an unbroken chain stretching forever into the past and the future. But how could anything possibly carry over from one eon to the next? The answer may lie in the one thing that can persist through this cosmic reset: information. Penrose proposes that faint imprints, gravitational waves from colossal events in the previous eon, could survive the transition. These would manifest in the new eon as faint, circular patterns in the cosmic microwave background radiation, the afterglow of its own Big Bang. Some researchers believe they have found evidence of these very patterns, though the claim remains hotly debated. This idea creates a hidden dimensional connection not through space, but across cosmic time itself. Each eon is a separate epoch, a separate chapter in reality's book, yet they are all linked through this conformal bridge. It suggests that the information defining our universe, and potentially every universe that came before it, is eternally recycled, written into the fabric of each new creation. Two particles separated by a vast expanse of space can influence each other instantly. This spooky connection, which Einstein himself famously questioned, is quantum entanglement. Now, a radical theory proposes that this ghostly link is not spooky at all, but has a tangible physical shape. This is the ER equals EPR conjecture, a profound idea from physicists Juan Maldacena and Leonard Susskind. It suggests that two entangled particles are not communicating faster than light. Instead, they are connected by a microscopic wormhole. In the language of physics, an Einstein-Rosen bridge, which is a wormhole, is equivalent to an EPR pair, the foundational example of quantum entanglement. Think of the universe as a vast, higher-dimensional block of space. Our familiar three-dimensional world is like its surface. Now, imagine 2 points on that surface. If they are entangled, they are not just linked by an invisible signal. They are literally connected by a tiny, tunnel-like structure that plunges through the higher dimensional bulk, creating a shortcut through the geometry of reality itself. Entanglement, in this view, is not a mysterious force. It is the physical geometry of space-time manifesting in a way we are only just beginning to understand. The bridge itself would be unimaginably small and unstable, far too tiny for any object or signal to ever traverse it. This is why we never see a violation of the cosmic speed limit. Nothing actually travels through the wormhole. The connection is built into the fabric of the universe, a permanent stitch in the quilt of space-time that instantly correlates the particles on either end. This stunning idea provides a potential solution to one of physics' greatest paradoxes, the black hole information paradox. It suggests that information falling into a black hole is not lost forever because it remains connected to the outside via a web of entanglement woven from these microscopic wormholes. The fabric of reality might be held together by an endless, invisible network of bridges, making our universe a single, deeply interconnected whole. This ghostly network of wormholes seems to stitch the cosmos into one piece, but it introduces a terrifying possibility at the edge of a black hole. The black hole information paradox strikes at the heart of physics, creating a direct conflict between two pillars of our understanding. On one side, we have Einstein's general relativity, which describes the event horizon as a smooth, unremarkable space. An astronaut crossing this point of no return would feel nothing special, at least initially, before being stretched into spaghetti by the immense tidal forces. On the other side, we have quantum mechanics, which insists that information can never be truly destroyed. If you burn a book, the information in its letters is not gone. It is just chaotically scrambled into the smoke and ashes. In principle, you could reverse the process and reconstruct the book. But a black hole, according to general relativity, seems to be the ultimate information shredder. Anything that falls in is lost forever, its information seemingly erased from our universe when the black hole eventually evaporates through Hawking radiation. This is the paradox, the smooth spacetime of general relativity and the information conservation of quantum mechanics cannot both be correct. Something has to give. To resolve this, physicists proposed a shocking and violent solution, the firewall hypothesis. What if the event horizon is not a smooth gateway, but a blazing wall of high-energy particles? This searing curtain of fire would instantly incinerate anything attempting to cross, thus preventing any information from ever entering the black hole in the first place. The information would remain encoded on the surface, preserving the quantum rule, but at a horrific cost, completely violating Einstein's principle of a smooth, uneventful horizon. This is a desperate solution, and most physicists find it deeply unsatisfying. It feels like a declaration of war between our two most successful theories of reality. The true resolution likely lies in a more profound understanding of the event horizon itself, one informed by the holographic principle. If our universe is indeed a holographic projection, then the information about everything that falls into the black hole is not lost inside its volume. It is smeared and stored across the event horizon's two-dimensional surface like data on a cosmic hard drive. The three-dimensional interior of the black hole, with its crushing singularity, might itself be a projection from this vibrating, information-rich boundary. In this view, there is no paradox because the information never actually falls into a hidden pit. It is just transferred onto a different part of the cosmic hologram where it remains preserved forever. The event horizon is not a destructive firewall or a simple doorway, but the very screen upon which the story of the black hole's contents is written. Hidden within the equations of particle physics lies a deep and elegant symmetry, a potential doubling of the cosmic cast. This is supersymmetry, a theoretical framework that proposes every fundamental particle we know has a hidden, super-powerful twin. The particles that make up our world are divided into two families. Fermions, like electrons and quarks, are the building blocks of matter. Bosons, like photons and gluons, are the force carriers that ferry information between matter particles. Supersymmetry posits a profound and beautiful link between these two families. It suggests that for every known fermion, there should be a superpartner boson, and for every known boson, a superpartner fermion. This introduces a whole new zoo of theoretical particles. The electron's superpartner would be the selectron, a boson. The photon's partner would be the photino, a fermion. The quark's partner would be the squark. While this might seem like an arbitrary doubling of complexity, it solves several of the biggest problems in physics in one elegant stroke. For instance, it provides a compelling candidate for the mysterious dark matter that holds galaxies together. The lightest of these superpartners, likely a neutralino, could be stable, invisible, and pervasive throughout the cosmos, perfectly matching the properties of dark matter. Furthermore, supersymmetry helps to unify the fundamental forces at extremely high energies, suggesting that the electromagnetic, weak, and strong forces were all one single force in the early universe. But where are all these superpartners? If they exist, why have our most powerful particle colliders, like the Large Hadron Collider, not produced them? The theory offers an answer. Supersymmetry must be a broken symmetry. This means that while the symmetry is perfect in the underlying equations, it is hidden in our low-energy world. The superpartners are not missing, they are just incredibly massive, so heavy that our current experiments cannot create them. This is where supersymmetry's connection to hidden dimensions becomes clear. It is a foundational pillar of superstring theory. The mathematics of strings only works if spacetime is supersymmetric. This requirement, that the equations remain unchanged when you swap fermions and bosons, is what forces the extra dimensions of string theory to curl up into those specific complex shapes. In this way, supersymmetry implies a hidden dimension not of space, but of particle relationships. It suggests that our entire catalog of particles is only one half of a grander, more balanced picture. A shadow world of superpartners that could be the key to unlocking the universe's deepest secrets, from the nature of dark matter to the very origin of dimensions themselves. Supersymmetry's elegant doubling hints at a deeper, almost unsettling truth about the cosmos. The same mathematical beauty that predicts superpartners also reveals a staggering cosmic diversity. This is the string theory landscape, a concept so vast it redefines the word possible. Within the framework of string theory, the way the 6 extra dimensions curl up is not unique. They can fold into an almost countless number of different stable configurations, each one called a vacuum state. A vacuum in this context is not pure emptiness. It is the lowest energy state of a universe, the background upon which everything else is built. The specific way the dimensions are folded determines the fundamental laws of physics for that universe, setting the values for constants like the strength of gravity, the mass of an electron, and the number of generations of particles. The number of these possible configurations is not just large, it is numbing. Physicists estimate the total could be around 10 to the power of 500. That is a 1 followed by 500 zeros, a figure so immense it exceeds the number of atoms in our entire observable universe. Our cosmos, with its 3 spatial dimensions and its specific, life-permitting physical constants, becomes just one single point in this unimaginably vast multidimensional landscape. We are not living in a specially designed universe. We are simply residing in one of the few habitable valleys in a cosmic terrain of near infinite possibilities. This landscape is not a physical place you could travel to. It is a mathematical map of potential realities, each with its own unique dimensional architecture and physical laws. Most of these universes would be sterile, with forces too weak to form atoms or too strong to allow for complex chemistry. Our existence is a testament to the sheer size of this landscape, for even in an ocean of hostile environments, a few islands of habitability were bound to emerge. This leads to a humbling thought. The very fabric of our reality, the forces that bind us and the dimensions we navigate, might be the result of a cosmic accident, a random roll of the dice in a game with 10 to the 500 possible outcomes. The search for extra dimensions has always pointed toward the impossibly small. But what if we have been looking in the wrong place? A revolutionary idea from physicists Nima Arkani-Hamed, Savas Dimopoulos, and Georgi D. Valley turned this assumption on its head. They proposed that some of these hidden dimensions might not be tiny at all, but could be as large as a millimeter across. To a physicist, a millimeter is an astronomical distance, vast enough to hold profound consequences for the fundamental forces. This bold proposal, known as the Large Extra Dimensions Model, directly tackles one of the most puzzling issues in physics, the hierarchy problem. The hierarchy problem asks why gravity is so unbelievably weak compared to the other forces. The electromagnetic force is 10 to the power of 36 times stronger. That is a 1 with 36 zeros after it, a difference in strength so colossal it seems unnatural. Why is the universe built with such a staggering imbalance? The answer, according to this theory, is that gravity is not inherently weak. It only appears weak to us because it is the only force that can spread out or leak into these large extra dimensions. Think of it this way. Imagine you are in a room with a single bright light bulb. If the room is small and confined, the light seems intense, illuminating everything. But if you suddenly find yourself in a massive, dark warehouse, that same light bulb would seem feeble, its light diluted by the immense space. In this analogy, the electromagnetic and nuclear forces are like that light bulb in the small room, confined to our three-dimensional brain and thus appearing intensely strong. Gravity, however, is the same light bulb in the gigantic warehouse of the large extra dimensions. Its strength is spread thin across a much greater volume, making it seem incredibly faint from our limited perspective. The true, fundamental strength of gravity might be just as powerful as the other forces, but we only ever experience its diluted, weakened shadow. This elegant idea reframes our entire search. Instead of building ever more powerful particle colliders to probe smaller and smaller distances, we might find evidence for these large extra dimensions by conducting exquisitely sensitive tabletop experiments that measure the force of gravity at sub-millimeter scales, searching for the moment when gravity's behavior subtly changes as we probe the edge of its hidden domain. This warping of space might be the key to solving one of the universe's greatest imbalances. the Randall-Sundrum model presents a brilliant and dramatic alternative to the idea of large, flat extra dimensions. It imagines our universe as a three-dimensional brane floating within a five-dimensional cosmos, but with a profound twist. The bulk space itself is intensely warped. This is not a gentle curvature, but a radical distortion described by a special type of geometry called anti-de Sitter space. Picture this warping not as a simple hill, but as a gravitational landscape so steep it fundamentally alters the strength of forces. Our visible universe, with all its stars and galaxies, resides on one brane, often called the TV brane because it is where the familiar forces of particle physics operate. Far away in the fifth dimension, separated by this warped bulk, lies a second brane, the Planck brane, which is the source of gravity's ultimate power. The warping between them is so extreme that it creates a natural exponential scale difference. Imagine a vast elastic sheet curved into a deep U-shape. If you place a heavy weight on one end of the sheet, it creates a severe dip. Now drop a single marble onto the opposite, high end of the sheet. From the marble's perspective on its flat section of the sheet, gravity seems very weak and it rolls only slowly. But from the perspective of the deep weight, the marble's gravity is incredibly diluted by the vast, curved distance between them. In the Randall-Sundrum model, we are like that marble living on our TV brane. The immense fundamental strength of gravity is generated on the distant Planck brane. But by the time its influence reaches us across the warped fifth dimension, it is exponentially suppressed, weakened by a factor of 10 to the power of 32. This single, elegant mechanism of geometric warping explains the hierarchy problem without needing any large dimensions at all. The fifth dimension can be incredibly small, yet the warping does all the work, shielding our world from gravity's true ferocity and creating the illusion of its feebleness. It suggests that the forces we measure are not absolute, but are local effects, entirely dependent on our position within a deeply warped, higher dimensional reality. That subtle pull between two plates in an empty vacuum might be our most direct window into the hidden architecture of reality. This is the Casimir effect, a bizarre and beautiful demonstration of quantum mechanics in action. In a perfect vacuum at the absolute zero of temperature, empty space is not truly empty. According to quantum theory, it is a seething, frothing sea of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence from the quantum foam, borrowing energy from the universe for an impossibly brief moment before annihilating each other and vanishing back into the void. Now imagine placing two perfectly smooth, uncharged metallic plates extremely close together in this vacuum, separated by a gap smaller than the width of a human hair. These plates act like walls, imposing a boundary condition on the quantum foam. Only certain wavelengths of virtual particles can exist in the narrow gap between the plates, while a much wider spectrum of wavelengths can exist outside them. This creates a pressure imbalance. The relentless activity of virtual particles pushing on the outside of the plates becomes greater than the push from the limited particles on the inside. The result is a net, measurable force that pulls the two plates together. It is a ghostly hand born from the nothingness of empty space itself. What makes this quantum curiosity so vital to our search is that this force is exquisitely sensitive to the geometry of space. The strength of the Casimir force depends directly on what wavelengths of virtual particles are allowed to exist, which is governed by the dimensions available to them. In our standard three-dimensional world, we can calculate the expected force with great precision. But if extra compactified dimensions exist, the calculation changes dramatically. The virtual particles would have more room to vibrate, additional ways to exist. They would not be confined to oscillating only in our three familiar dimensions. They could also wiggle in those tiny, curled-up, higher dimensional directions. This extra freedom for the quantum foam would alter the balance of pressure between the plates. The predicted Casimir force would become stronger or weaker in a specific, calculable way, depending on the size and shape of these hidden dimensions. Researchers around the world are conducting incredibly sensitive experiments, measuring the Casimir force between plates and nano-fabricated spheres at microscopic distances. They are looking for any deviation from the theoretical prediction for a simple three-dimensional vacuum. A single, consistent anomaly in their data could be the first tangible evidence that we are not alone in the void, that the vacuum we call empty is actually humming with the secret vibrations of a higher dimensional reality. It means the answers to the universe's biggest mysteries might not require a colossal particle collider, but could be revealed in the faint, persistent whisper of two plates drawn together in the dark. Deep beneath the border of Switzerland and France, scientists are staging the most violent microscopic collisions ever attempted. The Large Hadron Collider is not just a machine for discovering new particles, it is a powerful microscope, probing distances so tiny they might finally reveal the hidden architecture of space itself. One of its most thrilling quests is the search for extra dimensions, and it hunts for them in three primary ways. The first and most dramatic signature would be the creation of microscopic black holes. If extra dimensions are large enough, as some theories suggest, then the energy concentrated in a single proton-proton collision could, for a split second, warp spacetime so intensely that it pinches off into a tiny black hole. This would not be the planet-devouring monster of science fiction. It would be an ephemeral speck evaporating instantly into a shower of characteristic particles through Hawking radiation. Detectors like ATLAS and CMS are constantly on alert for this unique, explosive decay pattern. A second, more subtle search looks for the missing energy. This hunt focuses on the hypothetical particle of gravity, the graviton. In our familiar four dimensions, the graviton is incredibly weak and nearly impossible to detect. But if it can travel into the bulk of extra dimensions, then it could simply vanish from our brain during a collision. Physicists meticulously account for the energy before and after each proton smash. If a significant amount of energy consistently disappears without a trace, it would be a powerful hint that something, most likely a graviton, is carrying it off into dimensions we cannot see. Finally, there is the search for exotic resonances. If the extra dimensions are compactified, they impose a specific spectrum of vibrational modes, much like a guitar string has specific harmonic notes. A collision could excite these geometric harmonics, producing a heavy, unstable particle that decays in a unique, telltale pattern. Finding such a resonance would be like hearing a single, pure note from a hidden instrument, revealing the precise shape and size of the unseen dimensions. So far, the LHC has not found definitive proof. No microscopic black holes have blinked in and out of existence. No torrent of missing energy has been recorded. No exotic resonance has sung its unique song. But this absence is not a failure, it is a map. It tells us that if extra dimensions do exist, they are either smaller or more warped than our most optimistic models predicted. Each collision narrows the possibilities, guiding us toward a deeper truth about the fabric of our reality. While we smash particles together searching for hidden dimensions, the cosmos itself whispers of two deeper mysteries, dark matter and dark energy. These invisible components make up 95% of the universe's total content, yet we have no idea what they truly are. Could their elusive nature be a direct clue that we are not seeing the full dimensional picture? One compelling theory suggests that dark matter is not a strange particle in our universe at all, but the ordinary matter of a parallel reality. Imagine our three-dimensional brain floating in the bulk, with another brain floating just a tiny distance away in a higher dimension. The atoms, stars, and even galaxies on that neighboring brain would be completely invisible to our light and our telescopes. Their photons could not cross the gap to reach our eyes. However, gravity, the force that permeates the bulk, would not be stopped. the collective gravitational pull of that entire parallel universe would bleed through, influencing the motion of galaxies within our own. We would see stars whirling around galactic centers too fast, held in place by an unseen anchor, and we would call that anchor dark matter. In this view, dark matter is not a substance, but a shadow, the ghostly gravitational echo of a world forever beyond our reach. Then there is dark energy, the mysterious force causing the universe's expansion to accelerate. If our brain is dynamic, perhaps dark energy is the subtle pressure of the bulk itself, a force exerted by the higher dimensional space as it evolves. Think of the bulk as an ocean and our brain as a vast floating leaf. As the ocean currents shift and change, they could gently stretch the leaf, causing it to expand. From our perspective, trapped on the leaf, we would measure this as a mysterious repulsive force pushing every galaxy away from every other, an effect with no visible source. We call it dark energy, but it might be the slow, deep breath of a higher dimensional cosmos. These ideas reframe our greatest cosmic puzzles. The search for dark matter is not just a hunt for a missing particle. It could be an attempt to detect the gravitational presence of another universe. The force of dark energy is not a new law of physics, but a symptom of our universe's position within a much larger, multidimensional reality. The hidden 95% of the cosmos might be the most direct evidence we have that our familiar 4 dimensions are only a fraction of the true story. Our quest for hidden dimensions has led us through parallel worlds and cosmic brains, but one theory suggests we have been overcomplicating the answer. The mathematical universe hypothesis proposed by physicist Max Tegmark presents a vision of reality so simple and yet so vast it defies easy comprehension. It states that our physical world is not just described by mathematics, it is a mathematical structure. Every particle, every force, every law of physics is ultimately a mathematical object and a set of relationships within that structure. Think of a perfect, idealized circle. It exists as a mathematical truth, independent of anyone drawing it on a chalkboard. Tegmark argues our universe is like that circle, a concrete example of a mathematical pattern. He takes this idea to its ultimate, logical conclusion. If our universe is one mathematical structure, then all other self-consistent mathematical structures must also exist in just as real a way. This is his level 4 multiverse, a cosmos of staggering breadth where every possible universe governed by any coherent set of mathematical rules is out there, somewhere, in a state of actual physical existence. In this ultimate ensemble, universes with 4, 5, or 11 spatial dimensions are not merely theoretical possibilities. They are realities. A universe operating on the simple rules of Euclidean geometry exists alongside one built upon the bizarre algebra of octonions. There could be a cosmos where the number pi has a different value, or where the concept of time is entirely absent, replaced by a more complex mathematical relationship. Our particular home, with its 3 spatial dimensions, 1 time dimension, and specific force strengths, is simply one page in an infinite, unreadable library of mathematical existence. We do not exist within this universe, we are a pattern within it, a specific computation that the structure is performing. This idea pushes the anthropic principle to its absolute limit. We find ourselves in this particular mathematical structure not because it is special or unique, but because it is one of the exceedingly rare structures complex enough to allow for self-aware substructures like us to emerge and ponder our own origins. The hidden dimensions we have been searching for are not curled up in our space. They are simply the properties of other, equally valid mathematical worlds in the ultimate multiverse next door. What if the universe operates on a set of immutable laws not because it is fundamental, but because it is programmed? The simulation hypothesis proposes that our reality is not base reality, but an incredibly advanced construct, a digital simulation running on a computer of cosmic capability. While often discussed in technological terms, this idea takes on a profound new dimension when we consider where such a computer might exist and what its true nature could be. The substrate running the simulation, the ultimate hardware, would not reside within our four-dimensional spacetime. It would have to exist outside of it, in a higher dimensional reality where our universe is just one of many possible processes. The laws of physics we spend our lives studying, from the speed of light to the charge of an electron, would not be fundamental truths of nature. They would be the simulation's source code, the optimized rules written by the programmers to ensure the simulation runs efficiently and stably. Think of a sophisticated video game. The world inside the game has its own consistent laws of physics. Gravity has a set strength, objects have mass, and light travels at a certain speed. To a character within that game, these are the absolute, unbreakable laws of their universe. They have no access to the computer code that defines those rules, nor the electricity powering the machine, nor the physical room where the computer sits. In the same way, if we are in a simulation, our three spatial dimensions and one of time are simply the rendered output. The true action is happening on a higher dimensional plane, in a realm of pure information and computation that we, as part of the simulation, can never directly perceive. This perspective reframes the search for hidden dimensions. Finding evidence for extra dimensions would not just be a discovery about our cosmos. It could be the first clue that we are perceiving the output of a system whose inputs lie elsewhere. The puzzling fine-tuning of our universe's constants, the very thing that allows for complex life, might not be a lucky accident. It could be the result of deliberate calibration, a set of parameters chosen by the architects to see what kind of universe would emerge. This leads to an inevitable and haunting question. If our reality is a simulation, are we merely characters in someone else's experiment, or are we part of something even grander? A chain of simulations within simulations, stretching up through countless layers of dimensional reality. The silent, empty space between our world and another is not a void but a realm of its own, known as the bulk. This higher dimensional expanse is the true stage of reality, a cosmos where our familiar universe is merely one surface adrift in an immeasurable sea. The physics governing the bulk would be unlike anything we know, a grander set of laws where our four-dimensional spacetime is just a special case. In this profound emptiness, gravity might be the dominant force, weaving its geometry through dimensions we cannot fathom, while other forces remain trapped on their respective branes like stains on a collection of floating leaves. The very nature of time could be different there, perhaps flowing at a variable rate or existing as a static dimension, making the bulk a place of eternal, dynamic geometry rather than a narrative of cause and effect. Within this vastness, our brane is likely not alone. Other branes of various dimensions could drift through the bulk, some parallel to our own, others intersecting at strange angles. These could be entire universes with their own particles, forces, and laws, forever invisible because their light is confined to their own dimensional surfaces. A four-dimensional brane floating nearby would be a universe of incomprehensible complexity, a reality where beings could move in a direction we cannot even point toward. The interactions within this crowded higher dimensional sea could be the source of the most dramatic events in our cosmic history. A gentle ripple in the bulk, a gravitational wave from a collision of distant branes, might manifest in our universe as a sudden, uniform heating of the cosmic microwave background. A more violent encounter, a direct brane collision, could be the very engine of a Big Bang, resetting the cosmos in a fireball of unimaginable power. Even the mysterious dark energy pulling our universe apart might be the subtle pressure of the bulk itself, a deep, ambient force stretching the fabric of our brane from the outside. We are like fish in a pond, only now beginning to suspect that the water we swim in is just one layer of a far deeper and more mysterious ocean. Time itself may be the most familiar yet mysterious dimension of all. We speak of it flowing like a river, but physics paints a far stranger picture. In Einstein's theory of relativity, time is woven together with the three dimensions of space into a single fabric, spacetime. This four-dimensional block is static and unchanging. Within this block universe, the past, present, and future are not sequential. They all exist simultaneously, laid out in their entirety. Your birth, your life, and your eventual death are all equally real, fixed points in the cosmic landscape. The feeling of a flowing present moment is just that, a feeling, a subjective illusion as our consciousness glides along a single, predetermined track through this eternal structure. This challenges our deepest intuitions about free will and reality itself. But what if we take this idea even further? Some theories, like certain versions of string theory, entertain the possibility of multiple dimensions of time. Imagine a reality with two temporal dimensions. In such a universe, causality, the fundamental rule that cause must always precede effect, would completely break down. Events would not be connected in a simple, linear chain. An effect could loop back and become its own cause. You could potentially remember the future or encounter versions of yourself from a timeline that has not yet and may never come to pass. The stability needed for life, for coherent thought and consistent physical laws, would likely be impossible. Our single, arrow-like dimension of time may be another anthropic selection, a necessary condition for a universe complex enough to ask why it has only one. We are not just living in a specific place, but at a specific time, and that very fact might be the most important dimensional constraint of all. Our relentless march through time might be the universe's most convincing illusion. Deep within the quest to unite general relativity with quantum mechanics lies a mathematical monster, the Wheeler-DeWitt equation. This formidable formula was one of the first serious attempts to apply quantum rules to the entire cosmos to describe the wave function of the universe itself. But it yielded a shocking result. The variable for time simply vanished from the equation. In this fundamental description of reality, there is no t for time. The equation describes a static, frozen block, a universe where nothing ever happens. This is the problem of time, a profound paradox that suggests the flow of time is not a fundamental feature of the cosmos, but something that emerges from a more complex, timeless foundation. Think of a completed movie on a DVD. The entire story is there, encoded on the disc from the opening scene to the final credits. Every moment exists simultaneously in a static, unchanging state. This is the universe according to the Wheeler-DeWitt equation. When you play the DVD, you experience a flowing narrative, a sequence of cause and effect. The emergence of time in our experience is like hitting play. Our consciousness, our interactions with the world, create the persistent illusion of a moving present moment, scanning through the frozen blocks of a predetermined reality. But where does this illusion come from? One compelling idea is that time emerges from the intricate relationships between quantum particles in a vast, higher dimensional network. Your perception of now could be a consequence of how every atom in your body is entangled with the atoms in your environment, creating a localized, consistent sequence of events from a timeless whole. The universe does not evolve in time. Time is what we call our limited perspective on a reality where everything just is. This strange disappearance of time points toward an even more radical idea that space-time itself is not the foundation of reality. Deep within the calculations of particle physics, a new geometric shape has emerged, one that challenges our most basic assumptions about the universe. This is the amplituhedron. For decades, predicting the outcomes of particle collisions has required agonizingly complex mathematics, involving billions of virtual particles interacting across vast stretches of space-time. The amplituhedron, discovered by physicists Nima Arkani-Hamed and Jaroslav Terenkaye, sweeps this complexity away. It is a jewel-like geometric object that exists in an abstract, higher-dimensional space. To calculate the probability of how particles will scatter after a collision, You do not sum up endless Feynman diagrams tracing paths through spacetime. Instead, you find the volume of this single, beautiful shape. The answer simply falls out of its geometry. The implications of this are staggering. The amplitude-hadron's calculations are not only vastly simpler, they are more fundamental. They produce the correct results for particle interactions without ever referencing two of the core concepts we thought were essential to physics: locality and unitarity. Locality is the principle that particles can only interact if they are at the same point in space. Unitarity is the rule that probabilities must always add up to 1. The amplitude-hadron shows that these concepts, which are woven into the very fabric of spacetime, might not be fundamental laws. They could be emergent properties, side effects that pop into existence from a deeper, non-spatial reality. Imagine trying to understand a movie by studying the individual pixels on your screen. You would get lost in a sea of color and light. But if you could step back and see the entire script, the story would become clear and simple. The amplitude-hadron is like that master script, our experience of a universe with a continuous spacetime where objects interact locally might be the pixelated version, the rendered output of a far simpler, more elegant geometric truth that exists beyond space and time. This suggests that the dimensions we navigate, the very stage of our existence, are not the main event. They could be a useful illusion, a user interface projected from a realm where concepts like where and when have no meaning at all. The pixels of reality might not be tiny strings or grains of space, but bits of pure information. This is the startling vision of the information theoretic view of reality, a concept often summed up by the phrase "it from bit." Proposed by physicist John Archibald Wheeler, this idea flips our understanding of the universe on its head. What if particles, forces, and even spacetime itself are not the primary ingredients of the cosmos? What if they are all secondary phenomena emerging from something even more fundamental, the yes or no answers to a cosmic series of questions? In this view, every particle interaction, every flash of light, every event is fundamentally a transaction of information. An electron exists here and not there, answering a binary question. A photon has this polarization and not that one, registering another bit. The universe, at its most basic level, could be a vast, ongoing computation, and the world we perceive is the output of that computation. This seamlessly connects back to the holographic principle we explored earlier. If a three-dimensional world can be fully described by information stored on a two-dimensional surface, then perhaps that surface is the primary reality, and our four-dimensional spacetime is the projected image. The information comes first, the geometry of the universe comes second. This suggests a truly digital foundation for cosmology, where the continuous flow of time and the smooth expanse of space are approximations of a deeper, discrete reality. Think of a digital photograph on your screen. It looks like a continuous, high-resolution image, but if you zoom in far enough, you see it is actually built from individual, binary pixels. Our reality might be the same. The smooth, classical world described by Einstein is the high-resolution picture, while the underlying quantum realm is the pixel level, a frenetic dance of information exchange. This leads to a profound question. If the universe is fundamentally a network of quantum information, then what or who is processing the data? Are we simply patterns within the computation, living in a cosmos that is, at its heart, a cosmic manifestation of mind-bogglingly complex code? Perhaps the ultimate hidden dimension is not out there in the cosmos, but right here within our own minds. For centuries, we have treated consciousness as a byproduct of the brain, a ghost in the three-dimensional machine of our skulls. Yet, a growing chorus of thought suggests this might be backwards. What if consciousness is not generated by the brain, but is instead a fundamental property of the universe, and the brain is merely a receiver, a biological antenna tuning into a specific dimensional channel? This is the core of panpsychism, the idea that mind or experience is a basic and ubiquitous feature of reality, present even at the most fundamental levels. In this view, an electron might possess a tiny spark of proto-consciousness, a raw, minimal experience of existence. The complex consciousness we experience is not created from inert matter, but emerges from the sophisticated integration of these countless microscopic mental aspects. This radically reframes our search for hidden dimensions. If consciousness is fundamental, then the three-dimensional world we perceive is not the absolute stage of reality, but merely the particular broadcast our biological hardware is built to decode. Our neurons, constrained by evolution to navigate a world of solid objects and cause and effect, filter out the full spectrum of existence, presenting us with a simplified, survival-oriented user interface. We are like a radio that can only pick up one station, unaware of the entire electromagnetic spectrum humming all around us. An even more specific and controversial theory takes this idea into the quantum realm. The Orchestrated Objective Reduction Theory, or ORCH, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that consciousness arises from quantum computations happening inside the neurons within structures called microtubules. These tiny protein scaffolds could maintain quantum coherence, and when this coherence collapses, it gives rise to a moment of conscious experience. The theory goes further, proposing that this collapse is a bridge between the brain and a deeper, non-computational level of reality, a Platonic realm of mathematical truth. If true, this implies that our conscious awareness is intrinsically linked to a domain that exists beyond our familiar space-time, accessing a dimension of pure information and geometry. This forces us to confront a dizzying possibility. The solid, three-dimensional world we take for granted might be a collective hallucination, a consensus reality generated by billions of biological receivers all tuned to the same limited frequency. Our perception of a universe with three spatial dimensions and one of time could be a profound limitation, a filter born from evolutionary necessity. What if, freed from this biological hardware, consciousness could perceive the higher dimensional bulk directly, or experience the timeless mathematical foundation of the amplituhedron? We are left wondering if the final frontier is not space, but the very nature of perception itself, and whether the key to unlocking the cosmos's hidden dimensions has been inside us all along. The ultimate goal of physics is a single, elegant equation that describes everything from the dance of quarks to the whirl of galaxies. This is the dream of a theory of everything, a final framework that unites all forces and all particles under one roof. Our journey through these 30 theories is not a collection of disconnected ideas, but a series of glimpses at different pieces of this grand puzzle. Each concept, from the tiny curled-up dimensions of Kaluza-Klein to the vast, warped bulk of the Randall-Sundrum model, represents a different angle of attack on the same fundamental mystery. They are all attempts to answer the same profound question: what is the true, fundamental nature of reality? The concept of hidden dimensions in all its forms has proven to be the most resilient and powerful theme in this quest. It is the thread that connects the vibrating strings of superstring theory to the holographic projection of our reality, and from the parallel worlds of the brain multiverse to the emergent spacetime of loop quantum gravity. Whether these dimensions are compactified into microscopic loops, stretched across millimeters, distorted by intense warping, or simply illusions that arise from a deeper information-based reality, they offer a common language. This language allows us to reframe our greatest cosmic puzzles. The weakness of gravity is no longer a bizarre anomaly, but a clue that it operates on a larger stage. The mystery of dark matter might be the gravitational shadow of a nearby universe. The Big Bang itself could be the aftermath of a collision between dimensional membranes. A successful theory of everything would not make these ideas obsolete, it would weave them together. It would show how the holographic principle is compatible with the granularity of loop quantum gravity, and how the cosmic landscape of string theory gives rise to the specific, life-friendly physics of our particular brane. The search is not for a winner among these theories, but for the deeper synthesis that makes sense of them all. This grand synthesis would finally reveal how the countless facets of our universe, from the certainty of gravity to the randomness of quantum mechanics, are all manifestations of a single, coherent truth written in the hidden dimensions of existence. We have traveled from the tiny, curled-up dimensions of Kaluza-Klein to the vast, holographic projections of our cosmic horizon. We have witnessed collisions of Branes birthing universes and pondered if our reality is a simulation running on a higher dimensional computer. This incredible journey through 30 mind-bending theories reveals a single, unifying quest. The search for hidden dimensions is not merely a technical puzzle for physicists. It is a fundamental human drive to understand why anything exists at all. Each theory, from the elegant loops of string theory to the granular fabric of space-time, is a different path up the same mountain, all seeking a view of the ultimate truth. The very fact that we can conceive of these possibilities, that we can use mathematics and imagination to peer beyond the veil of our four-dimensional experience, is a testament to the power of the human mind. So we turn this final question over to you. Which of these visions of reality resonates most deeply? Does the cosmic hologram capture your imagination, or does the rhythmic cycle of conformal cosmology feel more true? Share your favorite theory in the comments below and let us know what cosmic mystery we should explore next. Subscribe to continue this journey with us as we keep unraveling the greatest secrets of the cosmos, one dimension at a time.